Topic 9, Electric Fields. Part 2, Electric Field Lines. Refresher on different types of fields. You are already familiar with gravitational fields and magnetic fields. Similarly, there are also electric fields. This is the gravitational field, which is uniform as indicated by these evenly spaced field lines. The gravitational field strength is symbolized by G. Now there are two ways of looking at G. One is the one that you're familiar with, which is acceleration due to gravity, and it's equal to 9.81 meter per second squared. Here we look at G as gravitational field strength, and it's equal to 9.81 Newton per kg. And here we have an object of mass mkg in this gravitational field, and it experiences a gravitational force of W, or weight. So weight is the gravitational force acting on an object. And the formula for linking weight to mass is this one here, W equal to mg. You're all familiar with the magnetic field around a bar magnet. What I want to point out is this. The direction of a magnetic field line at any point is determined by placing a north pole there. For example, we put a north pole here to determine the direction of the field line at this point. This north pole will be repelled by the north pole of the magnet to the right in that direction. So the direction of the field line at that point is to the right. Likewise, this north pole will be repelled by the north pole of the magnet along this line, this way. Now when you put a north pole here, this time the opposite happens. This north pole will be drawn toward the south pole that way. This north pole likewise will be drawn toward the south pole this way. So all the field lines go into south pole and come out of north pole. Just as in the case of magnetic field, we use north pole as a test pole. In the case of electric field, we use positive charge as a test charge, like this one here. So this test charge will get repelled by this positive charge to the right. So the electric field goes to the right at that point. Likewise, if you put a test charge here, it will get repelled along this line, and so on. All these lines like this going upwards. You can decide for yourself where the strong field is and where the weak field is. This time we use a positive test charge around a negative charge. So this positive test charge will get drawn towards the negative charge. So the field line is going into the negative charge, and likewise every field line goes into the negative charge. This is what the field lines look like when you place two positive charges close to each other. You can see that these field lines repel each other away. When you put a positive charge and a negative charge close to each other, this is what the field lines look like. So instead of repulsion, now there is attraction, and all the field lines join up these two charges together. This is what a uniform electric field looks like. This metal plate here is positively charged, and this metal plate here is negatively charged. And the field lines always go from positive to negative. This slide here is very much a summary of the previous few slides. It says here, electric fields can be represented by electric field lines. Field lines have directions. The direction of a field line is the direction of the force on a small positive charge placed at that point. The positive charge on the field line, as shown here, will experience a force that will move it along the field line. So this positive charge here will get moved along this line here all the way like this. Definition of electric field from the dictionary. You have to memorize by heart. Electric field is a field of electric force that any electric charge in that field will experience. Electric field strength, symbolized by capital E, at a particular point is the force per unit positive charge acting on a stationary point charge. In the diagram below here, a positive charge of 1 coulomb at point A here is experiencing a force of 2 newtons to the right, as indicated by the arrow. So, the electric field strength at point A is 2 newtons per coulomb, and written this way. So in short, if you want to find out how strong the electric field is at a particular point, you just put a 1 coulomb positive charge there and see what force it experiences, and that will give you the electric field strength. Formula of electric field. Based on the definition of electric field strength mentioned on the previous slide, we can write the formula as E equal to F over Q. E stands for electric field strength, measured in newtons per coulomb. F stands for electric force, measured in newtons. Q stands for electric charge, placed in the field, and is measured in coulombs. Rearranging the formula will become this way, making F the subject. Here is an example to show you. A small charge of that many coulombs, positive charge, experiences a force of that many newtons in an electric field, and you have to calculate the electric field strength, or how strong the field is. So E is the subject, and put the numbers in, you get that electric field strength, and it's in the direction of the force. But for B, because the charge is negative, so the force is going in the other direction. That's why there has to be a negative sign here, which means it is against the direction of the electric field.